include the field K, which has characteristic 0. We'll assume this in the following. Let X be a projective variety, and F from X to itself be a dominant rational map. We denote this KIAS. We denote this KX sub F to be the field of F invariant rational functions on X. That means if this phi is a rational function on X, we require this phi satisfy F pullback phi equal to phi. This pullback means composition. Phi composed with F. If a rational function phi satisfies this condition, phi composed with F equal to phi, then this phi is the element in this KX sub F. We assume this pair XF satisfy KX sub F equal to K. That means there are no non-constant rational functions. And there are two conditions. 1.1 is there exists one closed point such that the forward orbit is well defined and directly dense in X. This well defined means for each S greater or equal than 0, F is well defined at F X. This is a classical version. But as we know, if X has if this pair XF does not has a non-constant rational function, then for another pair YG birational to this one, the pair YG does not have constant rational function also too, but this orbit may not be preserved under this birational morphism. So we have the extend the conjecture to 1.2. It's a strong form of the first one. For every directly dense open set U of X, there exists a closed point whose orbit is well defined, contained in U, and directly dense in X. The conjecture 1.2 is birationally invariant. And we will see this later. Okay. If we have one dense orbit, we want more such orbit, but the density topology is not stronger to satisfy this condition. As pointed by Junyi Xie, we need the adelic topology on this xk. First, we assume the transcendent degree of this k over q is finite. I will not give the precise definition of the adelic topology. Instead, I'll give some properties. The adelic topology is stronger than the dielectric topology. It's also T1. The morphisms in the Euro sense are continuous for the adelic topology. And in particular, the endomorphisms are open. Another point is the irreducible components in the dielectric topology are preserved in the adelic topology. The last point says the Galois group action is continuous with respect to the adelic topology. By this point 5, we know when X is irreducible, the intersection for finitely many non-empty adelic open subsets of X is also non-empty. So any two non-empty open sets must have an intersection. This implies when dimension x greater or equal than 1, the identical topology is never Hausdorff. Using this notion, Dr. Junyi Xie proposed the following conjecture. Assume the transcendent degree of K over this Q is finite, and X is a irreducible variety, F is a dominant rational map. As before, we assume the F invariant rational functions are just a constant on X. Then there exists a non-empty identical open subset A, such that for every point X in A, its forward orbit is well defined and directly dense. Yeah. Note we also want the orbit to be directly dense, not adelic dense.
Sorry, excuse me. May I ask a question?
Yeah.
So since you did not define the adelic topology, so may I ask what about the P1 Q bar? What is the adelic topology on P1 Q P1? What are the open sets?
Yeah, on P1,
you mean it has more open sets than the Zariski?
Yeah.
So
even for P1, it has more open sets.
So it means its open set can be P1 minus countably many finite points. Is that true?
Yes.
Okay. Okay, thank you.
We have the following remark. The conjecture 2 is stronger than the conjecture 1. Yeah. Even in the conjecture 2, we require the transcendent degree of K over this Q is finite. But by a result of Junyi Xie, we know if we can show conjecture 2 for all such K, then the conjecture 1 holds true. Let's look at some known cases of the two conjectures. The conjecture 1.1 was proved by America and the Campana when the base field K is uncountable. Yeah, if K is countable, it has only been proved for some few special cases. The first one is conjecture 2 is proved for splitting endomorphisms of P1 to the power n by Junyi Xie and Thomas Tucker. In the case X is abelian variety or semi-abelian variety, and F is a dominant rational map. Conjecture 1.1 was proved by Filka, Scalar, and Satriano. Also, in the abelian variety case, conjecture 2 was proved by Junyi Xie. When this X is an algebraic surface and this F is a birational self-map, means the degree of F generally equal to 1. Conjecture 2 was proved by Junyi Xie. Moreover, when this X is a smooth projective surface and F is a surjective endomorphism, Junyi Xie also proved this conjecture 2. Our work generalized the smooth cases to singular cases. First, we give some preliminaries for the main result. Let X be a projective variety over K and F a dominant rational self-map. We see this pair satisfies the ZD property if conjecture 1.1 holds true. Strong ZD property means conjecture 1.2 holds true. And for AZD property, when the conjecture 2 holds true. And the last one is the SAZD property. This means for this pair, there is a non-empty identical open subset A, such that for every closed point x in A, the forward orbit OFX on the F is well defined and the Darcy dense in X. Yeah. Let's see this. In the conjecture 2, we assume the KIAS cube F equal to K. Then we have this long claim. But in the SAZD property, we don't assume the KIAS sub F equal to K. So in particular, the SAZD property implies the AZD property. That means in that case, the KX F equal to K automatically holds true. Because otherwise, there cannot be a Darcy dense orbit for this F. And so we face some notation. We denote this n sub 1x, the space of Arcadia dividers modulo numerical equivalence, and n sub 1x is the space of one cycles with coefficients in R modulo numerical equivalence. And nefx is the core of nef classes in n sub 1x. This n bar x is the core of pseudo-effective classes in n sub 1x. By result of Professor De Qizhang, we have a natural embedding of n sub 1x to n sub 1x. So in the case, x is q factorial, which means the multiple of v divider becomes a Cartier divider. So in that case, we can identify this n sub 1x with n sub 1x. Since we know the nef cone is contained in the pseudo-effective cone. In that case, the pseudo-effective cone is identified with this model cone, n bar x. So in that case, we have this include nef x contained in n bar x.
So your dimension 2, x is surface.
Yeah, surface.
Oh, okay.
Again, some definitions. Let F from X to itself be a surjective endomorphism of a projective variety. Then we define the first dynamical degree. Delta F is the spectral radius of this endomorphism. F up star acts on this n sub 1x. Yeah, the spectral radius means the maximum of the moduli of the eigenvalue of this linear transform. It's known that the degree of F less or equal than delta F to the power of dimension x. The other notation is the polarized. We see the map F is delta polarized if F pullback of H linear equivalent to delta H for some integer delta greater than 1 and ample Cartier divided H. By normal condition proposed by Dr. Shengmeng and Professor De Qizhang, we know this is equivalent to this one. F pullback of B numerical equivalent to delta B for some rational number delta greater than 1 and the big R Cartier divided B. Yeah, because this big divider is interior point of the pseudo-effective cone. Equivalently, we can suppose F pullback of B numerical equivalent to delta B for some delta greater than 1 and the big Q Cartier divided B. Actually, in this case, this relation f pullback of b numerically equivalent to delta b implies this delta is an algebraic integer. Yeah, this one holds for q KIAS divisors. We consider that this narrow several group with coefficient in q. We know this delta is also a rational number. This a rational number and also an algebraic integer implies this delta is an integer. So all the three conditions are equivalent. We have another definition. Still assume this F is a surjective endomorphism and X is a projective variety. We see this F is amplified if F pullback L minus L is ample for some KIAS divisor L. We see this F is inamplified if F pullback L minus L equal to H for some ample KIAS divisors L and H. It's clear from the definition, inamplified implies amplified. Yeah. There is another equivalent condition for F being inamplified. This is proved by Dr. Shengmeng. Yeah. This is F is inamplified if and only if all the eigenvalues of this linear transform F up star X on N over 1X are of modulus greater than 1. This is lemma. This lemma is collected from different papers. Yeah, they are proved by Dr. Shengmeng and Professor Qi. Let Fi from Xi to itself be surjective endomorphism, and we have another generally finite dominant rational map denoted by pi from x1 to x2, such that pi composed with f1 equal to f2 composed with pi. This means x1 to x2, x1, x2. This is f2, this is f1. We have this commutative diagram. Then in this case, the f1 and f2 have the same dynamical degree. Delta f1 equal to delta f2. And f is delta polarized if and only if so is f2. Yeah. The last one is if f1 is delta polarized, then every eigenvalue of this linear transform f1 up star x on n1x has modulus equal to delta. By our definition, this delta is integer greater than 1. This delta is for some integer greater than 1. So combine this with the equivalent definition of inamplified, we know polarized implies inamplified. There is also another remark. This is proved by Dr. Shengmeng and Professor Qi. If f is inamplified and the dimension of f is greater or equal than 2, then degree of f greater than delta f. This is because all the eigenvalues of this f of the f upper star on n1x is greater than 1, and the degree of f in some sense is a product of some of the eigenvalues. So in particular, degree of f is greater than 1 of the modulus of the eigenvalue. Okay. Now we can state the main result. Since we know when this f is a birational morphism, and Dr. Jun Yixie proved this pair xf satisfies the AZD property. It's conjecture 2. So we focus on the non-isomorphic case. Let f from x to x be a non-isomorphic surjective endomorphism, and then we assume this x to be a normal projective surface. The first claim is x has only log canonical singularity. If the canonical divisor KIAS is pseudo-effective, then the case 1 occurs. If KIAS is not pseudo-effective, then after replacing this f by an iteration, we may run a f equivalent minimum model program from x1 to this xr, then to this 1. Each step contracting a kxj negative extreme array. Yeah. From xj to xj plus 1, this morphism is a divisorial contraction, and the last one, xr to this 1, is a final contraction. Yeah, such that one of the following cases occur. The first one is f is quality top, and we can lift this f via finite downward cover to another surface V, and yeah, this V may be a abelian surface or elliptic curve product with a curve of genus greater or equal than 2, or P1 cross E. This E is an elliptic curve, or it's a P1 bundle over elliptic curve. Yeah. The second case is this Y is a smooth projective curve of genus greater or equal than 1. Also, this F descend to an automorphism of finite order on this one. Case 3 is Y is an elliptic curve, and X to Y is a P1 bundle. Yeah, from X to this Y is a P1 bundle. Case 4, this Y is isomorphic to P1, and we have FXR equivalent and finite surjective endomorphism XR to this Y cross P1. And the descending endomorphism is splitting. Case 5 is Y isomorphic to P1, but this F is polarized. And there is a F inverse stable reducer divisor S, such that KX plus this S purely equivalent to 0. Yeah, also by a result of Nakayama, we know in this case we can find F equivalent coordinate finite gamma cover V to X with this V a P1 bundle over a elliptic curve. For case 6, this Y isomorphic to P1 and F is polarized. Then we can show there is equivalent commutative diagram. In this diagram, we have this X and Y. This pi is the computation for this contraction. And then we have another elliptic curve E, homomorphism to this Y. And X delta is the main part of the normalization of the fiber product X cross E over this Y. We know this pi delta will be a P1 bundle. And this pi is just a P1 fibration. Yeah. Also, this mu X is coordinate top. Then we have the case 7. This XR is a full final type. And there is a FXR equivalent bidimensional morphism from XR to another surface X bar. Yeah. X bar is a KLT final surface with picard number 1. Also, we know I claim every XG. Yeah, this XG is the intermediate part of the memory model program is a rational surface whose singularities are KLT. The remaining two cases, we have this Y is just a point. For case 8, we have this XR is a projective cone over an elliptic curve. And the normal, since XR is a projective cone, we have a rational map from XR to the base elliptic curve. Yeah, and so this one induces another rational map X to this E. Our claim is the normalization of the graph of this X rational map to E is a P1 bounded, and F leads to this this P1 bounded gamma, such that the pullback action of F restricted to gamma is a scalar multiplication. The last case is rho XR, the Picard number of XR equal to 1, minus KXR is ample, and every XG is a rational surface with LC singularity and the rational singularity. Yeah. This is the structure theorem for non-isomorphic surjective endomorphisms of projective surface.
Excuse me, can I ask a question?
Yeah.
So what's the difference? Sorry, previous page. So what's the difference of 0.5 and 0.6?
0.5 and 6.
Yeah, both seems to be a double cover, cos eta double cover. Your x tilde, your v in 5 is your x tilde in 6.
Yeah.
And your E is the elliptic curve. Pi tilde is also a P1 bounded. So what's the difference?
I divide this in 2 points, in 2 cases because they come from different reasons.
But the results are the same, right? Because both are
P1 bounded. Yeah.
For 0.5 you have S, but 6 you don't have S, right?
Yeah, correct. And notice our structure theorem is very long, so I have this corollary, which is a refined version of the main theorem. Let F from X to X be a non-isomorphic surjective endomorphism of a normal projective surface X. Then, after replacing this F by iteration, one of the following 4 cases occur. The first is this F has X has a F invariant non-constant rational function. This comes from the maybe come from case 1, and clearly the case 2 implies X has a non-constant F invariant rational function. Yeah. The case 2 is F leads to an endomorphism on X prime. We are generally finite surjective morphism. Yeah, in this case, this X prime is either an abelian surface or a P1 model over an elliptic curve. Only 2 possibilities. Case 3 is F descends to an endomorphism on P1 cross P1. Yeah, and the descending endomorphism is splitting. It means commute with both projections. We are generally finite surjective morphism. The last case is some kind of long. F descends to an endomorphism on this X bar, which is a normal projective surface via birational morphism, such that the Picard number of this X bar equal to 1. Since our F is non-isomorphic, and the descending is via birational morphism, we know the F on this X bar is also non-isomorphic. Since the Picard number of X bar equal to 1, we know this F X bar is polarized. And by lemma we stated before, we know this X this F is also polarized. Another point is the anti-canonical divisor minus KS bar is ample Q-cardiac divisor. And this X bar is a rational surface with LC singularity and rational singularity. Yeah, this means either X has a F invariant non-constant function, or this F can be lifted to a smooth surface. And this smooth surface means abelian surface or P1 bound over inverted curve. Or F descends on P1 cross P1. The other case is F descends to a normal projected surface with P1 number 1. Yeah. Use this main theorem and the corollary, we can have the following applications. The first one is let F be a surjective endomorphism of a projective surface. And we don't require this F to be normal. It's just a projective surface. It's by the universal property of normalization, we can lift the original F to the normalization of this X. To define our algebraically closed field K, we assume the transition degree of K over this Q is finite. Then this pair XF satisfies the AZD property. Yeah, this means either there is a F invariant non-constant rational function, or there is a adelic open subset A such that for every point in A is forward orbit is directly dense. And we remarked before, we know the AZD property. If we can show the AZD conjecture 2, then we can obtain the conjecture 1, which means the same assumption on this X and F, but we don't require this K has a finite transition degree over Q. It's arbitrary closed field with the characteristic 0.
Hey, yeah, I have a question. So in this main theorem, so now you don't assume F is a non-isomorphic surjective.
Yeah.
So,
we can see that
now was
we have this result proved by Jun Xie. When X is an algebraic surface, F is birational.
Yes, so you don't cover his result. So in that case, you apply his result, right?
Yeah, correct. Yeah.
Okay, thank you.
So for every algebraic closed field, K with characteristic 0, you know the pair XF satisfies the ZD property. Actually, in this case, this one should be the strong ZD property, which means the conjecture 1.2 holds.
I still have another question. So again, so if you assume F is an isomorphism, then do you have an analog of the previous structure theorem? You have because you also have some kind of equivalent minimum model program for surface. If your F is an isomorphism.
Yeah. In that case, if F is isomorphism, then we can take the resolution of this X, right?
Yeah.
Automatically, this F lift to the resolution of this X. But in that case, we don't have this structure theory for this. What kind of this resolution of X can be. I mean, if this F is isomorphism, then we can take the resolution for this X. Since this F is isomorphism, sorry. In that case, we cannot leave this F to a morphism.
No, you can. No, you can. We only have a birational.
Yeah. In that case, we use the result. Where this F is of degree 1, we have the equivalent resolution. So we take this equivalent resolution. Yeah. It's up to that.
But I guess there is no equivalent minimal program for FTR type. Because you may have, because the exceptional curve may not be preserved under automorphism. There are infinitely many exceptional curves. So maybe the equivalent minimal program does not work for automorphism, I guess.
So when we apply the EMMP, we assume this have to be non-automorphism. Since our motivation is from the subsidence orbital conjecture, and in that case, we reduce to the smooth surface case. So I didn't consider this degree 1 case.
Okay, so the hard case is rational surface, smooth. So that one, I get Junyi Xie did. Rational surface, that's the key, the only case. MMP does not apply, yeah.
Yeah, but Junyi Xie does not give a classification for this endomorphism.
Oh yeah, I see. Okay, yeah. P2 might be the difficult case.
Yeah. So let's look at the second theorem. Yeah. So this one should be the strong DD property. Yeah. So either there is a F invariant rational function, non-constant rational function, or for every subsidence open set U, there is a point, a closed point, whose forward orbit is contained in U, and the subsidence in X. Since our F is a morphism, of course, this orbit is well defined. In particular, this implies this F has infinitely many subsidence orbits. And we can take different U. Yeah, so I will go a sketch of the proof of our structure theorem. In our structure theorem, we assume the endomorphism F will be non-automorphic. Then X has only LC singularities. This is proved by a lot of authors, such as Wao and Nakayama and this BFF. In particular, this implies the canonical divisor KIAS is a Q-Cartier divisor. If this KIAS is pseudo-effective, also by a random lemma, we can show in that case, F is called tau. Yeah, this lemma says when we have a endomorphism of a projective variety, and the canonical divisor is pseudo-effective and Q-Cartier, then the ramification divisor is 0. So this f is quasi-tall. And in that case, we apply Nakayama's result. Let this X be a normal projective surface. Then X admits non-isomorphic quasi-tall surjective endomorphism if and only if satisfied this pair satisfied one of the following conditions. There is a lift mu from this V to X. Either this V is a abelian surface or elevated curve product with a curve of genus at least 2, or P1 cross E or P1 bounded. But in our case, we assume this case pseudo-effective. So only case 1 and case 2 may occur. Since for the other cases, the KIAS is not pseudo-effective. This implies the case 1 occur when KIAS is pseudo-effective. When this, if this KIAS is not pseudo-effective, then after replacing F by a power, we may run the minimum bound program equivalently to get a final contraction XR to this one. Then we have this graph. Since the last one from XR to Y is a final contraction, X is a surface, so dimension of Y either equal to 1 or 0. If dimension of Y equal to 1, then we know this Y is a normal projective variety. And the dimension Y equal to 1, so this Y is a smooth projective curve. We can use the genus as a indicator for this one. The first case is gy greater or equal than 2. And we know this Y is of general type, and the endomorphism is isomorphism and has a finite order. So this G is of finite order. The other case is gy equal to 1. Y is a elliptic curve. In that case, we can use this proposition. F is a non-isomorphic surjective endomorphism, and pi from X to 1 is a P1 formulation. And the base Y has genus greater or equal than 1. So either this G is automorphism or genus of Y equal to 1 and pi is a P1 model. We can apply this because the final contraction is a P1 formulation in our case. This is a genus Y equal to 1. So when you focus on the case genus of Y equal to 0, then we have two possibilities. The first one is F is not polarized. In this case, we can show this X has no negative curve. Because if X has a negative curve, we can show the in that case, X has a negative curve. We can show this FR to be polarized. Yeah. So we know X has a no negative curve. Also, a general result of the dynamic degree is the delta of F greater or equal than delta of G. So if delta of F greater than delta G, by a result of Dr. Sherman and Professor De Qijang, we know this F descends to a splitting endomorphism of y cross p1. So we need to focus on the case delta f equal to delta t. Also, we have this long proposition. We suppose that x to p1 is f equivalent fundamental contraction with the delta f equal to the dynamic degree of the base. In that case, we know the Picard number of x equal to 2. So the net point is generated by two extreme rays with the generator of G and F. This F is a general fiber. So we know one of the following cases occur. Either there is a equivalent split, there is a equivalent and finite surjective endomorphism from x to p1 cos p1. And the descending endomorphism on this p1 cos p1 is splitting. The other case is f is coordinate but not polarized. Since f is coordinate, we can again apply Nakayama's theorem. There is a lifting via coordinate Galois curve. The last case is f is polarized. So in this case, this divider D, we can show this divider D is nef but not big. And we can choose this D to be irreducible reduced and F inverse stable, such that this KX plus D Q linear equal to 0. Then another result of Nakayama shows we can lift the endomorphism F to this V, where this V is a P1 bundle over an elliptic curve, and that the new pullback of D is a disjoint union of two cross sections. Since along this line, F is not polarized. Only case 1 and case 2 occurs. Yeah. Case 1 is F descend to a splitting endomorphism. Case 2 is this one is F coordinate. This is all the possibilities in the case F is not polarized. Then we focus on the case Fi is polarized. In that case, we can show this X has a KOG singularity. Yeah, this is a general lemma hold for projective surface. F is a surjective endomorphism of projective surface X. And we have a F equivalent fibration from X to this Y, such that the degree of G greater than 1, then this X has a KOG singularity. Since we know the degree of G greater than 1, this F cannot be a this F is non-automorphic. So X has only LC singularity. And the LC center is F inverse invariant. If we get a LC center, then use this invariant diagram, we can show in that case, we can show this point X. I'll write it. X is LC center. then this point is F inverse invariant. Also, in that case, X is not in the ramification divisor of F. This is proved by process something and Horry. X is not in the ramification divisor. And we know this X is F invariant. So this X maps to another point Y in the base Y. And we know the G inverse Y equal to this Y. This means this fiber is preserved. The fiber over this Y is preserved by F inverse. Yeah. So the pullback is degree of G times X1. This means this fiber over Y is ramified, containing the ramification divisor. So X must contain the ramification divisor. It's a contradiction. So the capital X cannot have LT center. So X has a KLT singularity. X is KLT. Then we also have two cases. X has no negative curve, or X has a negative curve. If X has no negative curve, then we can also apply this proposition. But in that case, F cannot be quasi-tau. Because we assume this KX is not pseudo-effective, so KX is not trivial. If F is quasi-tau, then F rising to some F pullback of KX is a multiple of this KX. If F is quasi-tau, we should get this one, but the ramification divisor is 0. This means the KX is numerically trivial. Yeah, this contradicts our assumption. So we only have the descent to a splitting endomorphism, or we have another divisor D such that KX plus D Q-linear equal to 0, and there is a lifting such that this V is a pure model over elliptic curve. The other case is X has a negative curve. Then we can contract this negative curve, get this X to this X bar. We use RF to denote the ramification divisor of this one. Ramification divisor of X FR, this pair. Then we use RFR prime to denote this one minus the negative curve C. If C does not intersect this one by a result of Masawa and Yoshikawa, we can get this equivalent commutative diagram. If this C intersect this FR prime, then we can show this X bar has only KLT singularities, and it's a final type. This is the case for dimension of Y equal to 1. If dimension of Y equal to 0, then we know the minus KXR is ample, and all these FGs are polarized. And by a result of process and Gongyo, we know either this XI is a projective cone over a limited curve or a rational surface with only rational singularities. Use this diagram, we can show the structure theory is true, but it's not very clear. We have classified all the cases and reordered them in the 9 cases. Use this main theorem, we can show the JD properties of the pair XF. We need this key lemma, which is proved by Junyi Xie. Let X be a reducible variety over K, and F is a dominant rational map. Then the following 3 conditions are equivalent. The pair XF satisfies AZD property equivalent to the XFM satisfies AZD property, also equivalent to this statement. There is another pair YG birational to XF, and this YG satisfies the AZD property. Also, this statement holds true for SAZD property. This is the key lemma. Let's see our corollary. In this corollary, we have the 4 cases for this non-orthomorphic endomorphism. If X has a F invariant non-constant function, then there's nothing to prove. So either this F lifts to a abelian surface or P1 bundle, or F descends to this P1 cross P1. And we know the abelian surface case is proved by Gilka, Scalar, and Satriano, also by Junyi Xie. So we need only focus on the P1 bundle case. Yeah, this P1 cross P1 is a trivial P1 bundle. The other one is the pickup number 1 case. In that case, we know this F X bar is polarized. In particular, this F X bar is inter-amplified. Now we will show the SAZD property holds in that case. Yeah, the first proposition is the row surface case. If we have a P1 bundle from a normal projective surface to this smooth projective curve 1, then this pair XF satisfies the AZD property. This is proved by Junyi Xie. The hard case is this one. Let X be a projective surface, and F is an amplified endomorphism, so that the degree of F greater than delta F. Then this pair satisfies the SAZD property. Yeah. We know that this SAZD property is stronger than AZD property. In particular, we know if F is inter-amplified or polarized, then this pair satisfies the SAZD property. This proposition is roughly proved by the following. By result of this Guji, we know if we have an endomorphism satisfy degree greater than the first dynamic degree, then there exists a repelling periodic point of this F. In that case, we can show either XFN satisfies the SAZD property or it has a good fixed point. This good means for each fixed point, we have an endomorphism on its tangent space. This good means the 2 eigenvalue of this endomorphism on tangent space is multiplicative independent and has modulus small or equal than 1. Then using some local dynamical, we can show the amplified plus this good fixed point implies there uses invariant neighborhood. Use this invariant neighborhood, we can show this pair XF satisfies the SAZD property.
Can I ask a question?
Okay.
Is this good fixed point is a smooth point of X?
Yeah, smooth point, of course. Yeah.
Okay, thanks.
Actually, Jun Yixie used this to prove the pickup number 1 case in smooth case, and this proof works for the singular case because this kind of discussion is local. We focus on the smooth good fixed point.
Okay, I got it. Thank you.
Okay. I think I have end my talk. Thanks. Okay. Any question?
Okay, thank you. Oh, sorry, I just muted my voice. Okay, any question? I have a question. Previous page.
This one?
Yeah. In your first proposition, you assume that f is amplified and the degree f greater than delta f. Why you have the assumption degree f greater than delta f?
Actually, we assume this because we want to apply this goodest result. We want to find a repelling periodic point of this f.
But I guess for surface case, if degree f greater than delta f, then it is automatically anti-amplified, I guess. Because delta f is you mean you can find a net eigenvector, right? F pull back delta f equal.
But he only assumed amplified. It's amplified. So maybe f is an automorphism, right?
But for automorphism, you cannot have degree f greater than degree f cannot greater than delta f.
Oh yeah. So he only assumed amplified endomorphism.
I don't think I think even amplified is not necessary. If degree f greater than delta f, then automatically it is anti-amplified, I guess.
Oh, okay. I see.
Because you have the minimal eigenvalue delta f. By Hodge index, you have d plus d minus have intersection. So delta f, so delta f delta f should be equal to degree f. So degree f greater than delta f implies delta f is greater than 1. So by the criteria, it must be here. So I guess amplify here is not needed. You only need to assume degree f greater than delta f.
Yeah, I think so.
Or maybe you use the amplified to use Fakrutin to say there are Zariski dense periodic points to find the smooth good fixed point, right?
Yeah.
Okay. Any other question? Okay, if no, let's thank the speaker. Okay, very clear. Okay.
Thank you.
Thank you. Okay, so our last speaker is Sho Yoshikawa. Okay, next week. Okay, see you next week. I'll end this talk. Okay, see you.
See you.